Hello everyone, thanks for coming. My name is Aitor and I am second year PhD student. Since the last talk was about tensor network, I think this will be easier to follow. The title of this study is Comparative Analysis of Classical and Quantum Inspired Solvers, a preliminary study on the weighted mascot problem. Okay. This is the scheme I will follow for this presentation. And I will start with the motivation. The motivation of behind this study was to analyze three different perspectives to face the same problem. The first perspective was heuristics. With the population crossover and mutation, it explored the large solution space. The second one is the machine learning. We train a model and learns patterns in the weighted mascot problem instances. And the final perspective is the quantum-inspired one. We use tensor networks and DMRG algorithm, and we use this because nowadays we're in the NISQ era, and we think that tensor networks can serve as a bridge between quantum computing and classical one. Okay. The objectives of this study was, first of all, analyze the strengths of each paradigm for this problem. Also, we want to explore the tensor network capabilities of compression to the problem. And we want to provide insights about the strengths, limitations, and scalability of each paradigm. Here we can see the mathematical formulation of the weighted mascot problem and a possible solution for the graph. And in short, I have to say that the objective of the mascot is to divide a graph into two groups and maximize the weight between edges. Here we can see a bit string of a possible solution for this graph. Okay, now I'm going to explain the algorithms we use for each paradigm. In the heuristic, we use a genetic algorithm. We create from scratch a genetic algorithm, and we call it canonical genetic algorithm with these parameters. And we implement a genetic algorithm called genetic algorithm optimal catch from this work with these parameters. Okay. The second algorithm we use is a graph neural network. We use this because this neural network from this work with these parameters use the same formulation, the Kubo formulation, but has a different strategy for solving this. Instead of optimizing the solution, it tries to approximate one solution and learns about this function. And finally, we create an algorithm that is able to generalize any weighted mascot instance and map it to an MPO form. So we map our cost function to an MPO form and apply to this MPO the DMRG algorithm that minimizes this expectation value and returns a solution in form of an MPS. For our experimentation, we use a dataset that is publicly available. This dataset contains 15 weighted graphs, ranged between 10 and 250 nodes. And we run each solver 10 times to mitigate statistical bias. We record some metrics. The first one is the approximation ratio. Here is the formula. The R is the number of runs, in our case 10. The E sub R star is the energy obtained in each run. And the E sub G is the known ground state or the best known optimum. We also record the execution time in minutes and the memory usage in megabytes. Okay. Now, with this said, I'm going to show the table referring to the approximation ratio. First of all, we have the N, that is the number of nodes, and we have 4 boxes representing each algorithm. First of all, the MRG with different bound dimensions, then followed by the graph neural network. After this, the genetic algorithm with optimal cuts, and finally, our genetic algorithm, our canonical genetic algorithm with different population sites. Here, a higher number represents better result, and we can see, first of all, the approximation ratio and then the standard deviation. The best results are marked in bold, so if we look at this table, we can see that for the most of the cases, the DMRG gets the best approximation ratio, specifically using a bound dimension of 2. Okay, with these results, we perform a Friedman and MNG test, and this test has a statistical significance of p lower than 0.05 with a critical distance of 1.75. Here, a lower number represents a better result, and we can see that the winners are the DMRG algorithms, followed by the graph neural network, genetic algorithm with optimal cuts, and finally the canonical genetic algorithm. Okay. Then here we can see a table, the same table, but referring to the execution time in minutes. Here, lower number is better. So, and also the results are marked in bold. So here we can see that the DMRG with bound dimension 2 also gets the better results than the rest of the algorithms. And finally, we can see the table of the memory usage. Here also the lower memory is best, and here the winner is the graph neural network. After this table, we can conclude that the tensor networks outperform the rest of the methods, especially in quality of solution and execution time. The graph neural networks are the most memory efficient ones, and the tensor networks are the ones with higher memory demand. This is curious. This is strange because tensor networks are able to compress large matrices, but this is due to the application of the DMRG that needs to perform and store large matrix operations, and this is why the memory increases. And we pretend to extend this word. First of all, we want to include in the comparison more combinatorial optimization problems and also problems related to the real world. And we also want to include more algorithms in our comparisons for each paradigm and also include the quantum ones. This is all. Thanks for your attention.
Thank you, Aitor, for the nice overview. We can have a few questions. Okay, I actually have a quick one that I wanted to. I had one, if I remember it. So yes, I was wondering what choices of graphs did you take to test the performance of this algorithm? Because I was thinking that these DMRG methods usually are good for kind of local entanglement, but if you had a graph in which mostly everybody was connected to everybody, then I was wondering why DMRG would still be an efficient way to solve the problem.
I think this is problem independent, and the bound dimension will always be low because these problems do not have entanglement. The solution is a diagonal matrix, so all the possible solutions are in the computational basics. So with a bound dimension of 2, it's enough. And probably with about dimension of 1, you can also have better, same results and faster.
Okay, thank you. Then I would say we thank all the speakers of the session again.